Have you ever wondered why water is all around us and has been part of human civilization since we existed, yet we continue to have so many issues managing it? Right now, as you're watching this, somewhere in the world, a city is flooding. A farmer is watching their entire field of crops die, and a child is walking 2 hours just to find clean drinking water. These aren't just coincidences, and it's not all just bad luck. It's actually part of a pattern, an underlying system where humans and water are very deeply connected, where we have actually become embedded within the water cycle itself, shaping it in ways that can result in very unintended consequences. Welcome to Rivulay, where we explore coupled human water systems through science and real-world examples. We look at how human society and water have co-evolved together all over the world and throughout all of time to better understand the water challenges that we currently face today. In today's episode, we will explore what is a coupled human water system through the lens of socio-hydrology. Socio-hydrology is a relatively new scientific field of research which I've been studying over the past decade. But first, let's kind of set the stage for water. How much we currently try and handle it, and how much it still eludes us. We all know we need water. It makes up our bodies, we use it to grow our food, manufacture our goods, generate oil, electricity, and build infrastructure. Literally, everything that runs modern society runs on water. And for this reason, we spend a staggering amount of money trying to control it. Globally, we spend several $100 billion every year just on the physical infrastructure we need to treat and deliver water to our homes and cities and farms. These are things like pipes or treatment plants or irrigation lines. But when you consider all of the other things associated with water, like flood control systems, responding to water disasters, mitigating for drought, handling complex water rights across jurisdictions and politics, these things also cost an enormous amount of money. And when you add it all up, we're all spending a significant portion of our GDP every year across every continent and in every economy to try and keep up with water. Specifically, water-related disasters impact more people and cost more money than all the other natural disasters combined. Since the turn of this century, water-based natural disasters, so these are things like floods, storms, droughts, and even rainfall-triggered landslides, they've affected over 4.5 billion lives, over half the population. They've killed over 400,000 and caused at least 4 trillion in direct economic damages. These are the damages that we have documented directly right after the disaster. They don't include indirect losses that are much harder to quantify, such as reduced productivity or impacts to our physical and mental health or long-term economic slowdown. Not to mention the softer impacts on entire communities when they're forced to suddenly rebuild or relocate their entire lives due to this unmanaged force of water. In fact, water accounted for more than 3/4 of all natural disasters recorded this century. And over 90% of all the people affected by any natural disaster, they were affected by either too much or too little water. Not earthquakes, not wildfires, not tornadoes combined. Water. And beyond natural disasters, we know that over 2 billion people today, 1 in 4 humans alive, do not even have access to safe and reliable drinking water at home. Over 3 billion lack access to safe sanitation systems. As a result, billions and billions of hours are spent every year collecting water. This is time that could go to more productive activities like working or raising a family or going to school. And these aren't just faraway problems. Right here where I live in the United States, around 30 million people are served by water systems that violate federal safety standards, and over 2 million live without any running water or basic indoor plumbing. So why did I just give you all these super depressing statistics? It's not because I just want you to think we're doomed at all. It's because I want you to realize just how much money and focus we already are trying to spend on water and how bad things still are. And help you consider that maybe the way we've been doing things thus far could be part of the problem. When you put everything together, we're spending hundreds of billions of dollars a year on water, and we still don't have basic water security for every person alive. We're still getting hammered by disasters all over the world. We're still fighting over water with our neighbors. And we still don't seem to have enough water for all of our farmers to grow the food that we need. So what is going on? Why can't we figure this out? Do we just need to spend more money? Is water too big of a problem or too strong for us? Mother Nature? Is our engineering wrong? In part, sure. We can always focus more on water, and that would help things. And our engineering isn't necessarily the problem. I was a practicing hydrological engineer for about 10 years before going back to school, and they do a lot of really good things. But what I want to suggest to you today is that all of these problems with water that keeps eluding us as a society, it's part of this underlying dynamic, and it includes more than just the physical water itself and the hard infrastructure we build to try and manage it. There's actually a more complex system behind all of this madness, and it involves you and I, humans. So first, we need to go back to grade school for just a moment to better wrap our mind around what all of this means. And let's revisit the water cycle. We all learned it. You probably remember it, the classic water cycle. If you don't worry. We're going to get into it briefly here. So what happens in the classic water cycle is water falls from the sky as some form of precipitation. Some of it flows over the land, becoming runoff, gathering into streams and rivers, and those eventually go out to the ocean. Some of it soaks into the ground and becomes groundwater. Plants absorb some of it and release it back into the atmosphere through transpiration, and the rest generally evaporates, condensing into clouds and falling again. A nice little elegant closed loop system, all driven by energy from the sun. And it had been running this way for well over 4 billion years, basically from the dawn of water on Earth until more relatively recently when us humans entered the picture. You see, around 10,000 years ago, we went and figured out agriculture. And with this came the first deliberate large-scale manipulations of the water cycle by humans. We started digging these irrigation channels to move water from the rivers over to our irrigation fields instead of it going directly to the seas. We cleared out forests in order to plant more crops, and so this changed how water naturally wanted to move through the landscape. Less of it was intercepted by tree canopy, and more of it started kind of rushing across the surface, and eventually different patterns started to emerge underground. Over time, we started pumping a lot of this water up from the ground, and all of these things fundamentally altered how the water cycle behaved. It's no longer driven by just natural physics-based cycle, that humans are deeply involved. Today, humans have actually built over 60,000 large-scale dams or reservoirs around the world. We do this to systematically capture water so that we can use it when we want to use it and release it to fit our schedule rather than Mother Nature's. The amount of water that can currently be stored in just these large-scale reservoirs is roughly 1/5 of all the water that flows through the world's rivers each year. Think about that for a moment. We're holding back a significant fraction of the planet's fresh water Water that would otherwise naturally enter the oceans or be intercepted and become groundwater. Humans have not only borrowed from the water cycle for our own needs, but we've become an embedded component within it, actively reshaping how fundamental laws of nature play out across space and time. And yet, this water cycle diagram that we all learned in school still treats water as a purely natural system, governed entirely by physics, chemistry, thermodynamics, but no human agency in the equations at all. In other words, this diagram suggests that the way water moves across the earth is driven primarily by things that we can touch and measure. Things like soil or vegetation, an aquifer, the flow of the stream. These are all physical and observable and much easier to quantify than humans. And when you frame the system in this way, the implication is that, in theory at least, we could go out and measure all of those pieces of natural physical things in really high enough detail. Every soil type, every plant, every drop of water. And if we strung enough of that detail together, we could fully describe the system using physics-based equations, model them, and predict a physical outcome. And in that way, we could kind of control the system in a very top-down, technocratic manner. In science, we call these kinds of systems Newtonian, meaning they operate according to classical mechanics, such as those established by Sir Isaac Newton in the late 17th century. These kinds of mechanics are highly deterministic, so they're driven by universal laws that allow for very precise prediction. Causality in these systems is linear, meaning A plus B always equals C. And I can attest, being an engineer for a number of years, this is definitely how we modeled the water cycle. This is how we designed detention ponds. This is how we figured out if your community was going to flood and what to build to protect you. This is how we modeled for agricultural irrigation and getting domestic potable water to your home. We used this kind of thinking. And even right now, hydrologists sometimes add in non-deterministic things such as stochasticity or nonlinearity, fancy words meaning they try to iterate things and bring in some elements of surprise naturally. But in doing so, they're still treating the system as fundamentally physical. It's water, water in, water out. Humans are more of kind of a boundary condition on these kinds of stochastic, updated systems. They still act on the system from the outside. They're not deeply embedded within it. But as you heard from the statistics in the introduction, water doesn't seem to act in that way. We try to manage it and model it and predict it and measure it, and it still keeps flooding us. We try to harvest it using all of these beautiful equations and models, and we still have mass drought and mass food insecurity. We try to address it through very strategic policies and laws, but we still have millions impacted every year by water conflict. So, what is going on? Why can't we figure out water? Some people will tell you this is all just a result of climate change, that water is too strong for us and everything's unprecedented and we're never going to be able to manage it all. Or that there's a lack of funding or political will. We just need more money, we just need more focus. And in part, those things are going on, but that's not the entire picture with water. Because these things are still, even at their core, very Newtonian issues. Weather and money. These are things that we could theoretically, physically model through equations where A plus B should roughly equal C. And what I want to suggest to you is that this framing is partially incomplete. Because the water cycle, even though it does behave physically according to classical mechanics, it's not purely a Newtonian system, especially because humans are inside of it and we've become part of it. And so when you consider that, these seemingly unsolvable collisions between society and water, what we start to see, at least this is the lens through what socio-hydrologists look at the system as, is we see something that's not as much Newtonian and a little bit more what we call Darwinian. A Darwinian system, on the other hand, is a system that is very dynamic and it's adaptive to internal changes within itself. So, in the sense of a coupled human water system, Darwinism means that the water is constantly responding to human interactions, but our human interactions are also constantly responding to water. And so we're co evolving together to come up with a much more complex and adaptive system. So these kinds of systems are not fully mechanical or deterministic. They're much harder to predict. You can still study them, you can still model them, but causality tends to be a bit looser, and the outcomes do not always add up to the sum of the internal parts. And so the reason this is important is because if you can accept that the system is Darwinian, then we can see that when we go into this complex system with all these human and physical water parts interconnected, and we go try to fix one little piece of it, even if we have the best of intentions, we may inadvertently trigger a ripple effect elsewhere throughout the system and impact society or water or both in an unintended fashion. This is because when humans are involved in a system as complex as a coupled human water cycle, we fundamentally bring in all of our internal complexity, such as our choices, our values, and our perceptions, and we're simultaneously shaped by it. The good news is that the water sector is starting to really embrace this concept and is expanding towards that direction by explicitly including humans within the water cycle. In 2022, for example, the United States Geological Survey released an updated water cycle diagram that explicitly included key human activities, things that we know shape water, things like agriculture, industry, domestic water use, reservoir storage, or stormwater runoff from more urban landscapes. So, releasing this diagram was a meaningful step forward. It acknowledged formally that humans aren't just passive observers of this natural water cycle system where we stand completely outside of it looking down, but instead we're active participants within it. And our actions matter and must be accounted for holistically. This understanding replaced a decades old understanding of the water cycle, which involved only natural processes we've already discussed. And now, with this more formal educational diagram, modern educators and students could start to see the water cycle more as this complicated system involving a mixture of both natural and human phenomena. And as a result, over time, it's become much more common to see high level water planning that uses what we call integrated water management. Integrated water management is a systems based approach where you might, for an example, connect a flood model with an economics model, or you might link a crop model with a hydrology model. And these things are really cool and exciting in their progress in the water world. But what I want to try to get through in this video as an understanding is that integrated is not the same thing as coupled. Integrated means we've taken separate models that have traditionally operated in these different silos and we've kind of connected them along their edges, like snapping together big Lego sets along the perimeter. So they start to share some data back and forth at their boundaries, But each Lego set still runs according to its own internal logic. And in these integrated systems, humans are still represented as these external variables that act on the water system, still trying to control it or change it from the top down. Coupled is fundamentally different. In a coupled system, the human world and the water world would be so intertwined that you cannot meaningfully separate them. Changes in the water cycle would reshape human behavior, and changes in human behavior would constantly also be reshaping the water. And those two-way feedbacks evolve over time. They actually co-evolve together, and they start to build up their own momentum and their own internal memory. And what's still missing from even our best integrated models are the human variables that are harder to quantify, which cause this deep internal tight coupling. But these variables that are harder to quantify, things we've started to touch on, we'll get into with some concrete examples soon, things like belief systems, perceptions, feelings, do actually drive how these coupled feedback loops play out. So these are things like whether a farming community trusts their government to save them during a drought, or whether a family knows if they're living in a flood zone, or maybe how a culture has related to a specific river for generations, and then what happens when that relationship changes. So these things like beliefs and values and politics and relationships, they aren't just soft add-ons. They fundamentally shape how the entire system evolves in ways that a purely physical model cannot predict. For most of human history, we did understand this more intuitively than we do now. Water wasn't always just a resource to use. It was actually power. In ancient civilization, whoever controlled the water controlled the power. It was a means of survival. It was a means of meaning. Think about for just a moment the last time you, specifically, were caught in a big storm, one of those thunderous, big, you feel them in your bones storms. Or you stood at the edge of a massive, monstrous roar of a river running really strong and fast. There's something that happens in your body, right? And in your mind. And this something, it's older than language. It recognizes that water has a force and it has its own agenda, but somehow our hearts and souls and ourselves are intricately connected to it. And so as you'll see throughout this channel, we try to build infrastructure and policies to try and manage that feeling, to try to control that water. But we can never quite shake it, and we can never fully control it. Because somewhere deep inside of us, we know water is visceral. Water is us. So, I hope you'll join me in this work. And if this video helped you even a little see the water cycle differently, please like, subscribe, and share. Thanks for joining me, and I'll see you around. Thanks. Bye.